Hello and welcome to this lecture. In the previous lecture, we saw this testing for the sample mean, which is the z-test, and we'll start looking at problems in this lecture. First few problems that we'll see will be sort of direct problems. The distribution will be given, the null hypothesis will be given, alternative hypothesis will be given. You have to find alpha, beta, and then you'll also have problems where maybe a situation is described and you have to write down what the samples are, what the hypothesis is, etc., etc. Okay, so we'll do that. We'll start doing that in this lecture. Okay, so in these problems we'll have to calculate the the Gaussian CDF once in a while. For that I have this Colab window open. So I have NumPy and SciPy stats, and anytime I want to run a normal PDF or CDF calculation, I'll come back to this window and get the actual value. Okay, so let's begin with the first problem. In this question, the distribution is normal with mean mu, which I guess is something we are going to test for, and a variance of 9. There are n equals 16 samples, and the observed sample mean is 10.2. Let's just quickly write down these things. H0 is mu equals 9.5, let's say. That's what's the first problem. HA is mu is greater than 9.5, so this is a right-sided test. So x bar is which is distributed as normal with mean mu, and the variance is going to be 9 by 16, isn't it? So remember the 9 by 16, that's the n, right? So you've got number of samples 16, so the variance is 9 by 16. This is an important step, don't forget this. Don't simply take the variance as 9. As you take more and more samples, the variance of the sample mean goes down, and the given value of x bar is 10.2, and your test is going to be, remember it's always good to write down the test. It's alternative hypothesis right-sided, so you're going to be rejecting H naught if x bar is greater than some c. Okay, and under this condition, what's going to be your type 1 error? What's the probability you reject H naught given that H naught is true? So this is probability that x bar is greater than c given that mu equals 9.5. Under that distribution, how will you reject H naught? So since this is x bar is mu, so in this case you know that x bar minus 9.5 divided by 3 by 4, right? What is 3 by 4? It's square root of 9 by 16, okay? So sigma square is 9 by 16. So sigma, this guy is sigma, this guy is mu, okay? So square root of that. This is the standard normal distribution. So this probability is going to be 1 minus, because this x bar is greater, right? So it's going to be 1 minus FC of c minus 9.5 by 3 by 4. Okay, so this is the most important calculation here. So now I need to equate this. Remember, I'm testing at a significant level of 0.05. I want my type 1 error probability to be 0.05. If you rewrite this a little bit, move things around and rewrite it, you will get c equals 9.5 plus 3 by 4 FC inverse of 0.95. Think about a couple of seconds how I got here. Move this to this side, you get 0.95. Take FC inverse, you will get c minus 9.5 by 3 by 4 equals FC inverse of 0.95. Just multiply and add, you will get this. Okay. Now it's a simple question of computing this. If you have to compute this, I normally use this. What do we call this? This is this Colab rough work type notebook here. So it is st.norm.ppf. So this is your FC inverse function, right? This is your FC inverse, and then this is your FC inverse. I'm multiplying it by 3 by 4, adding 9.5. If you run this, you will get something. You're getting 10.73. Okay, so 10.73. So that's the value of the threshold. So what are you going to do to the test? X bar is 10.2. It is lesser than this, so you're going to accept z test at alpha equals 0.05. It says accept H naught. That's what it says for this case. So you're going to conclude that the distribution mean in this case was 9.5. Okay. So contrast this with your approach for the p-value. Supposing you couldn't fix any significance level, you can't go ahead and fix c, right? In that case, you will try to make a decision based on the p-value. How will you find the p-value? Instead of c, you will put 10.2. Okay. So if you do that, what p-value do you get? If you do that, 10.2 by 3 by 4, isn't it? Okay. So if you run this, you're getting a p-value of 0.175. It's not low enough, right? So you need the p-value to be low enough if you want to reject null. So in this case, 0.175, you know, it's not that low, so that you can't reject it. Okay, so that's another way of doing the hypothesis testing, right? One is the significance level, fix the threshold, you have a proper test, you can do it. The other is, you know, no significance level fixing ahead of time. You just compute the p-value based on what you observed, and if it's low enough, you reject. In this case, we are doing significance level. So the other one is this other case where you know, the null hypothesis is mu equals 8.5 instead of 9.5, and the alternative is mu greater than 8.5. Everything else sort of remains the same. So the only thing that changes in this equation you will see is instead of 9.5, you have 8.5. So if you do 8.5 by 3 by 4 FC inverse of 0.95, you see instead of 10.73, you're going to get 9.73. Okay, and what is the z-test going to do at alpha equals 0.05? It's going to reject H0. Okay, because 9.73 is a 10.2 goes to the other side. If you were to compute the p-value, I mean, just to check that all these things sort of make sense at some level, you can go ahead and compute the p-value just to see that what would have happened in that case. Getting 0.01, maybe if you're thinking of p-value as 0.05, you know, you can see it's going down below that. So that's a connection there, 0.05 being the significance level, right? What's p-value? P-value is the lowest significance level at which you're going to be rejecting H naught. Clearly, if it works out below 0.05, you will reject at 0.05 also. Okay. So anyway, this is a straightforward calculation. These kind of problems are more or less formula computations. You should just be systematic, write down carefully, don't make silly mistakes with the variance. It's a very common mistake. Instead of 9 by 16, you may take 9, or you may take something else there. Just be careful in the calculation, and you'll get to the answer. It's very systematic. Any test you can do this. I mean, I'm doing it for the z-test. Tomorrow, if you have some other test where you know, you're rejecting null with some test, and then it's always alpha is always probability of rejecting null under the rejecting null under the null being true assumption. It's just a question of writing down that probability, whatever the distribution may be. In this case, the distribution was standard normal. In your other cases, you may get other distributions. You just have to write it down and repeat this same thing. So this is bread and butter calculation. You should be very comfortable with this. Okay, so here is a slightly different one. It's sort of you know, a word problem where the situation is described. You made an app for identifying faces, and you want 90% of the time the face to be correctly identified. So this is a slightly different distribution. There's nothing normal here. Every sample is like a photograph, and if your app correctly identifies, you get a 1, right? If or maybe the app correctly identifies, you get a 0, right? Or maybe you know, yeah, so let's say correctly identifies, you get a 1. If the app wrongly identifies, you get a 0, right? So that's the like a Bernoulli P distribution that you have, and you have 500 such photos. The app correctly makes identification for 462. Okay, and you want to do a z-test for the null hypothesis is p-value, the mean being 90, and whether it's greater than 90 at significance 0.05. So the distribution is slightly different. So let's just first write down samples. Sometimes if the samples are not clear, you need to write it down. X1 to X500. We can take this as Bernoulli IID, of course, IID Bernoulli P. Okay, and what is Xi? Xi is 1 if app is correctly identifies. Zero else. Okay, so this is what's given to you. These are the samples, and the sample mean in this instant ended up being 462, right? 462 by 500, okay, which is 0.924 as written down here. Okay, so that's what the sample mean ended up being. And what is your null hypothesis? Null hypothesis is p equals 0.9. Alternate hypothesis is p greater than 0.9. Okay, you would like to test against this. and your sample mean is this, and what is your test going to be? This is your right-sided test, so you will reject H0 if your x bar is greater than some c. Okay. Now, what's the distribution of x bar? You can sort of make a normal approximation here, because this is Bernoulli, it's a sample mean divided. The sum of all these things will be binomial, divided by n will also be sort of binomial divided by n. Its binomial is very closely approximated by normal. We've seen that before. So we'll approximate the distribution of x bar. So x bar, we will say, is normal with mean p. Okay, and what will be the variance? Variance is going to be p times 1 minus p divided by 500, isn't it? Sorry, square root of no 500. Variance is just divided by n, right? So hopefully that's okay. So this is sample mean. Okay, so each sample has mean p and variance p times 1 minus p, each xi. You add up all of them, divide by 500. Your mean is going to remain the same. Your variance will get divided by 500. So this is x bar. So in particular, x bar minus p by square root of p times 1 minus p by 500 is going to be my standard normal. Okay. So now what's my alpha calculation? Alpha is a probability that x bar is greater than c given p equals 0.9. What is that going to work out to? 1 minus fc of c minus 0.9, right, divided by square root of 0.9 times 0.1 is 0.09. So let's just leave it like that, 0.09 by 500. Okay, so I've just put p equals 0.9 here. 0.9 into 0.1 is 0.09 by 500. 0.09 square root is actually 0.3. So you can rewrite this if you like. I mean, so what is this? This has got to be 0.05. From here, it's so you know the same calculation as before, right? So 0.9 plus square root of 0.09 by 500 fc inverse of 0.95. By now, this calculation must start to look very, very familiar to you. Okay, so for the right-sided case, at least, this is very, very easy. So we got this. So here we got 0.3. I'm sorry. So 0.3. If you want, let me just write it as np.sqrt of 0.09 by 500, right? So exact same thing as what we did, plus 0.9. So that's going to be my threshold, and that works out to 0.922. Okay, let's go back to our screen. So that's 0.922, 0.922. Look how close it is to x bar. So since x bar is greater than c, right, 0.924 is greater than 0.922, the z-test at alpha equals 0.05 concludes that we reject the null. Okay, so we're going to conclude that the app is in fact greater than 90% in average prediction, correct prediction. So that's good news for the app, isn't it? So that's nice. You can say it's greater at significance level 0.05. Hope I didn't make any calculation mistakes here. I would be very careful in looking at this very carefully. So the distribution of x bar is usually the thing you have to worry about. I think it's okay. It's correct. So you can do p-value instead of this if you like. Instead of fixing a significance level, if you like, you'll get some p-value here. So maybe we can check that out also. What p-value would you get here if you do that? 0.924 minus 0.9 by the same big old np.sqrt of 0.09 by 500. Okay, so let's take it out. Okay, what did I do? I didn't close the bracket. Okay, 0.036. It's okay. It's low enough p-values, below 0.05. We know definitely it'll be below 0.05, right? Okay, So notice how if you reject at a significant levels of 0.05, the p-value will in fact be lesser than 0.0305 in some sense, right? Okay, so this is the kind of problem. Hopefully this gave you an idea. So you see how similar this is to the previous problem. Everything is just the same calculation, except that in this case you had to just work a little bit harder to find the actual distribution and write it down. Okay, so let's go back to another problem where it's maybe a slightly different alternate hypothesis, but more of a textbook problem where you just given the distribution, number of samples is given, and you have to just design the z-test carefully. Okay, so again, let me just go through this a little bit fast. The null hypothesis is mu equals 4. There are two different sets. So let's start with the first one, and the alternate hypothesis is mu not equal to 4. So this is a two-sided test. Okay, so if you're going to do two-sided testing, what is your test going to be? You will reject H0 if absolute value of x bar minus 4 is greater than C. Okay, so remember, notice how the test suddenly changes in character. So notice how I have to reject two sides, right? So this is the same as x bar greater than 4 plus C or x bar lesser than 4 minus C. Okay, so both cases. So 4 is sort of like your main thing. If you above 4 by too much or below 4 by too much, you're going to be ending up rejecting the null hypothesis. So it's sort of an obvious test. Okay, so pay attention to this. This is important. Okay, so now what is x bar? X bar is normal. Okay, with mean mu and variance 36 by 25. So notice once again that 25 will come in, that is your number of symbols. Okay, so so alpha is probability that you reject null. What is the probability that you will reject null? Absolute value of x bar minus 4 is greater than C given mu equals 4. Is that okay? So x bar is mu equals 4, and so notice here you will get x bar minus mu by 6 by 5 is the normal standard normal distribution. So I'm going to divide. So mu is 4. I'm going to divide both sides by 6 by 5. Okay, and this will just become maybe I'll write one more step here. Probability of mod x bar minus 4 by 6 by 5 is greater than C by 6 by 5. Okay, so this is under this mu equals 4. So you will have this to be 1 minus Fz of C. So this is the so I've done minus 4 here. So C is just C by 6 by 5. Okay, so what's inside this is the normal distribution. So what's the normal distribution? Greater than C by 5, 1 minus Fc of C by 5. Is that okay? Hopefully that's good. Notice how the test ended up being nicely written around 4. You have to pay attention to these kind of things when you have two-sided hypothesis. I'm writing down the test like this. Okay, so if you notice if it's one-sided, I'll usually simply write x bar greater than C. If it's right-sided, left-sided, I'll write x bar less than C. Two-sided, you have to pay attention. There has to be some center, and then x bar minus 4 has to be big enough. Okay, so this I'm going to equate to 0.05. Okay, so this will give you C equals much simpler, right? So 6 by 5 times Fc inverse of 0.95. So let's try this one. You're going to get what? There's no plus, it's just multiplied by 6 by 5, isn't it? That's nice. 1.97. Okay, so this works out to 1.97. Okay, so in this case, what has happened? The sample mean is 6.4, mod sample mean minus 4 is 2.2, which is actually greater than 1.97. So since 6.2 minus 4 equals 2.2 is greater than 1.97, okay, z-test at alpha equals 0.05 concludes that you reject H naught. So, this is not 4, mean it's not 4, it's maybe something not equal to 4, right. So, given that the sample mean was 6.2 at a significance level of 0.05. So, these are the sort of results you will get from hypothesis testing. Okay. So, you have to get used to how these results sound. Okay. So, the other hypothesis is mildly different. So, here in this case mu equals 8 and the alternative says mu is less than 8, it is left sided. So, what is your test going to be? You will reject H naught if x bar is less than C. So, notice the difference here. The distribution sort of remains the same, and your alpha calculation will go probability of x bar less than C given mu equals 8. So, this will work out as directly FC of C minus 8 by 6 by 5. Okay. So, this will have to be 0.05. So, notice how things change when you go to the left sided sort of testing. X bar has to be less than C given mu equals 8. Okay. So, for mean 8, this x bar minus 8 by 6 by 5 is a standard normal, and if it is less than C, it is just C minus 8 by 6 by 5. So, this probability is the same as this guy, FC evaluated at that 0.05. Okay. So, notice how this has changed. So, this will mean that C is actually equal to 8 plus 6 by 5 times FC inverse of 0.05, it is not 0.95. Notice how this has changed in sign and in difference. So, I will have to do FC inverse 0.05 multiplied by what? 6 by 5, I think, right, that remains the same, and then plus 8. So, if you do this, you are going to get 6.02, that is what you are getting, okay. You get 6.02, okay. So, you are rejecting if x bar is less than C, right. So, in this case what happens, since x bar equals 6.2 is actually greater than 6.02, your z test at alpha equals 0.05 will end up accepting H0, right. So, it is actually greater, it needs to be lesser for you to do it. So, let me just demarcate these two questions for you. Okay. So, the two questions and two calculations. So, hopefully you see the similarity in the calculation. Don't notice so much the differences between these calculations. The similarity is much more important. It is the same calculation. You write down the null, you write down the alternate, write down the test. The test will change depending on whether it is two-sided or right-sided or left-sided, and you find the distribution of the test statistic. That's the most crucial part. Find the distribution of the test statistic. Once you do that, it's just an alpha equals probability of rejecting null given that the null is true. And once you know the statistics of the test, right, what is the distribution of the test statistic, you can just compute the probability, whatever it may be. In this case, in the z test, it ends up being normal. You just have to get the standard normal involved. In other tests, we will see later on, this distribution will change. If it changes, just go look up the corresponding PPF or CDF or whatever function that you have. Okay. Hopefully, this drove home the point. We will see more problems in the next lecture. Thank you.